Hello and welcome to NPTEL course on Aero Engine Gas Turbine Cycles, lecture 3. In last lecture, we were discussing about the engine development cycle. We have discussed about the classification of the aero engines. We have discussed about the evolution of these aero engines. Very important, the derivation of the thrust equation using control volume approach and mechanical thrust by all these components. In terms of classification, we must have realized that gas turbines which are applicable for the aircraft are classified in terms of say turbojet engine, turbofan engine, turboprop engine, turboshaft engine. They all are having their own speciality. So, as and when we will be discussing, we will discuss everything in detail. In terms of derivation, we have realized we have taken our control volume approach, in which we have considered our solid boundary and our gaseous boundary. Based on that, we have come up with the equation for the thrust, and later on we have discussed about the mechanical thrust by all these components. So, let us retake for what all we were discussing in last session. In this, we have discussed about the thrust which is been generated by the compressor. I say it is in one direction. Same way here by my combustion chamber, that is also in the same direction as my compressor. My turbine, that is what will be generating the thrust in opposite direction. My nozzle, that is what will be generating the thrust in say opposite direction. So, in overall, if we look at, we can say the thrust we are dividing into forward thrust and rearward thrust. So, this forward thrust, that is what is having higher magnitude, and that is what it says, it is giving the movement of my aircraft in a forward direction. Based on this, we have asked to solve the numerical. So, this is what was a numerical that was given as a tutorial, and here we have given different numbers in terms of area, outlet velocity, pressure and mass flow rate at say different component entries, say maybe compressor, diffuser, combustion chamber, turbine, jet pipe and the nozzle. So, let us try to analyze this numerical. It says what all data is available with us. Say we know what is our mass flow rate, we know what are the velocity, pressure and area at the entry and exit of all these components. Now, we have our fundamental equation. It says the component thrust, that is given by pressure into area at the exit minus pressure into area at the entry plus m dot into V exit minus V entry. So, we will be calculating the thrust generated by all these components, then we will try to sum up all these thrust values and we will be comparing that with our fundamental equation, that is what is my engine thrust equation, and we will try to compare whether we are getting the same number or not. Okay. So, let us start by individual component step by step. So, very first component we will be selecting, that is what is say my compressor. For that we can write down, it is given by m dot into V2 minus V1 plus A2 into bracket P2 minus P1. So, here this is what is representing my stations 1, 2, 3, 4, 5 and 9. So, for entry condition, we have our value of mass flow rate, we have our exit velocity, no information, that is what is given in terms of flight condition or the ground condition. We are taking our V1, that is what is equal to 0. So, we can say our engine it is on the ground. The pressure at the entry also it is not given. So, we will assume say that pressure to be 0 Pascal, and pressure at the outlet, it is giving say this number. So, let us try to put this all numbers. If we are putting these numbers, it says the thrust which will be generated by the compressor is coming 84,421 Newton. It says this is a positive magnitude. So, we can say it is representing the forward direction. So, there you can see this is what is representing my forward direction. Now, let us try to look at the next component, that is what is connecting my compressor and combustion chamber. It is my diffuser. For the diffuser also the information which is available, my exit velocity is 112 meter per second, my exit pressure also is known to me, my exit area also is known to me. Let us try to put these numbers. If we are putting these numbers, it says the thrust by this diffuser, it is coming out 9811 Newton. Again this is having positive magnitude, means we can say this is representing the thrust in a forward direction. So, here you can see these two components which are having the positive magnitude and it is representing my forward thrust. The next component what all we have is my combustion chamber. For that combustion chamber also, let us try to put these magnitudes. So, here if we look at this, if I will be calculating, it says my thrust generated by the combustion chamber, that is what is coming on a higher side, it is higher value and that too it is having positive value. So, you can say the thrust which will be generated by the combustion chamber, that is what is in a forward direction. Now, here in this case we will be going with say the turbine. For turbine, as we have discussed, my exit velocity, that is what is having the higher magnitude. If we will be putting this as a number which are given, it says my thrust which will be generated by the turbine, it is coming negative magnitude with the higher number. If we look at this is of negative sign, that means my thrust by this turbine, it will be in the rearward direction. If we consider our next, that is what is say my jet pipe. For this jet pipe we can calculate the thrust. That thrust is coming again is a positive, that means it is generating the thrust in the forward direction. And the next component what we have is my nozzle, and for that nozzle if we are calculating the thrust, this is coming to be negative, that means my thrust will be in the rearward direction. Now, if we will try to put the total thrust, that is nothing but the summation of all these components, then the magnitude which is coming as 49,304 Newton, and that is positive, hence my thrust will be in forward direction. Now, what all we have studied from our basic fundamental equation, let us try to put the equation in terms of my thrust calculation. It says it is given by m dot into V 9 minus V infinity, and this is my P 9 minus P 1 into A 9, that is my exit area. If I will be calculating this, it says my thrust value which is coming exactly same as what all we have discussed with. So, now you can understand this is what is of real need, and we must realize all our engine components, they are generating the thrust. It is not that the thrust that will be generated only by my nozzle. Okay. So, what all conception or misconceptions we are having, that is what need to be rectified here, and we have proved that by both the way what calculation we have done for the thrust, they both are coming same. Now, let us try to understand how my pressure, that is what will be varying along my engine. So, here if we look at, this is what is representing my compressor, and for compressor we know my pressure, that is what will be increasing from entry to the exit of my compressor stage. That pressure we are representing in terms of my static pressure as well as my total pressure. Very soon we will be discussing what is the need of this static pressure magnitude as well as my total pressure magnitude. We have seen this diffuser basically is acting like a flow decelerating device. That means my static pressure, that is what will be say increasing. In my combustion chamber, my static pressure, that is what will remains constant, nearly constant. Then we will be having our turbine where it is going for the expansion, means my static pressure, that is what will be reducing. In my jet pipe, I can assume my static pressure to be constant, and in the nozzle where again my flow is getting accelerated, means my pressure will be reducing. And what all you are looking at in terms of the magnitude of my P total and P static, that is what is representing my jet velocity. Now, here we need to understand our fundamental equation, that is what it says, m9 into V9 minus V infinity plus this A9 P9 minus P infinity, that is what is representing say my pressure in all this component, that is what is varying at the entry as well as exit, and that is the reason why what all we are discussing, that is what is happening in terms of the contribution of the thrust that will be generated by the individual components. Now, let us try to look at what we mean. Suppose I consider say this is what is one of the device. It may be engine device, maybe compressor, maybe turbine, or maybe combustion chamber. So, for that what all understanding we have learned our first law of thermodynamics, and that is what has given us the important equation, that is what is called steady flow energy equation. Here I am representing that as my inlet and this is what is my outlet. Suppose if I consider there is no heat transfer, there is no work transfer, I will be having my M inlet, and that is what is my mass flow rate at the entry and mass flow rate at the exit. Based on my steady flow energy equation, I can write down my Q plus W plus this is my energy equation, where this is representing my internal energy, kinetic energy and potential energy. Since we have assumed there is no work transfer, there is no exchange of heat, so this equation will get simplified in this form. Now, further simplification, if we look at this H, that is what we can represent in terms of Cp into T, that is nothing but my enthalpy. And in this case, if we look at the final equation, that is what will be coming. It says my Cp into T plus V square by 2, that is what is constant. This is what is very important equation for us. So, let us try to analyze. Suppose say I want to measure my temperature. So, this temperature we can measure by using thermocouple or by using say thermometer, and what all temperature I will be measuring using this device. I say that temperature is my static temperature. I say this thermometer, that is what is moving with the air velocity. Now, let us try to understand in different way. If we consider my moving air is brought to the rest under say reversible condition. It is a special condition we can say, where all my kinetic energy of air that will be converted into internal energy, and this energy further it will be changing into heat energy that will be increasing my pressure and temperature of the air. Now, what all we will be measuring in terms of pressure or temperature, that is what is defined as a total pressure and total temperature. So, we need to understand here what all we are discussing about the property. We have property, that is what is called static property. We have property called say say total property. Okay. Now, let us try to analyze this in a different way. If we consider this gas turbine engine, the gas turbine engine is comprising of the turbo machinery. We can say compressor and turbine, they are the turbo machinery components, where we will be having this fluid velocity, that is what is very high, and hence the change of my kinetic energy from the entry and exit of each component, that cannot be neglected, that is not the small magnitude, and that is the reason why we are considering all our properties for the calculation as a total property. So, let me put the point here. When we will be analyzing our gas turbine engine, that is what is for say our cycle analysis, we are not interested in static properties, we are not interested in static temperature, we are not interested in static pressure, we are not interested in static density. What all properties we will be discussing, they all will be the total property. So, this is what we need to keep in mind. This is always a confusion with lot of literatures available in open domain. They are using static properties, but when we are discussing the aero engines, we need to be very careful, where we are more interested in total property compared to our static property. Now, we are interested in say thrust, because thrust, that is what is driving my aircraft, and for different flight regimes my thrust requirement, that is what will be varying. If I consider say takeoff, so for takeoff we are looking for maximum amount of thrust. So, we can say that is what is required in order to lift off your aircraft. So, just realize a very important criteria. When we are designing our engine, our maximum thrust is at the takeoff. So, engine need to be designed at the maximum thrust condition. If I am unable to take off my aircraft, then that engine is of no use. So, we need to be very careful. All engines basically they are designed at say maximum thrust condition, that is what is my takeoff condition, and this takeoff condition, that is taken as a design condition. When I am flying or when I am climbing, the requirement of the thrust, that is what will be reducing. When I say cruise condition at particular altitude, when we are flying, under that condition my thrust requirement will be minimum, and here we are more concerned with the fuel economy. As my thrust requirement is lower, you can say my amount of fuel requirement also will be lower, and that is where we are concerned with the fuel economy. Now, if we consider these engines, they are having application for the fighter aircrafts, where we will be doing all kind of maneuvers, where we are looking for variable thrust. So, there are special applications in terms of maneuvers, that is what is being done by fighter aircrafts, where the requirement of thrust will be different, and for that the special kind of engine design configurations are required. Sometimes we are moving with the acceleration and the deceleration of the aircraft. This is mainly when we are discussing about the fighter aircrafts, where we are looking for the variable thrust. During the descent, my thrust requirement will be lower, and during my landing, that is what will be less than that of my maximum thrust. So, here you need to be very careful. As we have discussed, we are having different kind of mission, we are having different kind of requirements, we are having different kind of application of these gas turbine engines, especially for different kinds of our aircrafts. Okay. So, mainly major concern, it is my maximum thrust requirement, that is what we say is my takeoff thrust. Now, let us try to analyze this equation. Suppose if I consider this is what is my thrust equation. Now, as per my requirement, I will say I want to fly at high speed, means my forward speed need to be increased. If I want to increase my forward flight, we can say my V infinity I want to increase. But at the same time, suppose if I consider my thrust requirement, suppose that is what is constant. So, in order to compensate that part, what we need to do is either we need to increase our mass flow rate, or we need to increase our exit velocity, or maybe sometimes we need to go with the increase of both M9 as well as V9. Now, this near constant thrust characteristic at any altitude, that is what is a desirable condition. We can say it is a flat rated configuration for the jet engines. Okay. Now, when we are flying at this near constant thrust condition, that is what is required, the higher thrust power for the forward speed. So, under that condition, the situation will happen that my aircraft will be flying with the turbojet engine, and that is flying at very high subsonic speed. Under that condition, the air that is what is going inside my engine, that will be facing very first component, it is called my inlet diffuser. So, this inlet diffuser that will be facing my supersonic flow. Under this situation, my thrust requirement also will be higher, and in order to compensate that part, we need to go with say afterburner. There is other alternative where it says there is no need of as such any turbo machinery. There is no need of compressor, there is no need of say your turbine. We will be using our ramjet engine, that is also called jet engines. So, we can say when we are looking for our flight condition from Mach 0 to say little less than say 3, we will be going with our turbojet engine, and beyond that we need to compromise with the performance, and under that condition we need to go with different kind of configuration. Now, let us try to understand the important criteria, that is what is called international standard atmosphere. So, here on right hand side, if you look at, this is representing the altitude, and this represents the variation of my density, pressure and temperature. So, if we look at carefully, the atmospheric parameter like pressure, temperature and density, that is what is changing with my altitude. The major change, that is what you are looking for, that is what is happening with my density and the pressure. And if we look at the temperature, it says because of absorption of my solar radiation of water vapor and subsequent radiation back to the space, we will be having the variation of temperature, that is what is happening up to certain altitude, and after that we will not be having much variation in terms of my temperature. So, standard sea level condition, if we consider these conditions are say 288.15 Kelvin, that is what is a sea level temperature. My sea level pressure we are considering 101.3 kilopascal, and density we are considering 1.225 kg per meter cube. So, in order to evaluate the performance of our aircraft engine, we need to go with this standard atmospheric condition. So, as and when required, we will be discussing how this parameter, that is what is affecting the performance of our engines. Now, let us try to analyze the equation what all we have. We say our net thrust, it is given by m dot into V 9 minus V infinity plus A 9 into P 9 minus P infinity. Let me introduce the terminology. Here I say this as my momentum thrust, momentum drag, my pressure thrust and my summation of momentum thrust and pressure thrust I am writing as a gross thrust and momentum drag. So, here in this case, suppose we are considering my mass flow rate, that is what is not varying. Let us consider say mass flow rate, that is what is constant. This is what is very important and that need to be understood clearly before going into the detail. So, in this case when I say momentum thrust, that is what we are writing as a m dot into V9. My momentum drag we are writing as a m dot into V infinity. My A9 into P9 minus P infinity, that is what we are representing as my pressure thrust. So, let us try to understand how these parameters they are varying with my flight speed. So, very first parameter let us take, that is what is my pressure thrust. So, pressure thrust it is represented in terms of area into difference of this pressure P9 minus P infinity. On an x-axis we are having the flight speed and here we are having my say pressure thrust. So, if we look at here, it says with change of my altitude, my magnitude of P infinity, that is what is changing. So, if we are going as we have discussed with altitude, my pressure that is what is reducing, that is what will be resulting in the increase of my pressure thrust. So, at different altitude with the change of my flight speed, we will be having different pressure thrust. Now, let us try to analyze the next term, that is what is my momentum thrust. This momentum thrust it is represented as m dot into V9, where m dot we are assuming to be constant and V9 it is my exhaust velocity. There is no straight relation with my flight speed. So, if we consider that as a configuration, my momentum thrust at different altitude, if I consider that is what is remaining constant. So, we are not having the variation of my momentum thrust with the variation of my flight speed. Now, let us try to analyze the next term, that is what is my momentum drag. This momentum drag it is represented as a m dot into V infinity. Since we have assumed this m dot to be constant and my V9 is flight velocity. So, you can say this is resulting in the change of my drag. This drag also is defined as a ram drag. We will be discussing this ram drag in detail in the next few lectures. So, here in this case we can say we are having the linear variation of this. So, here we consider say change of my altitude. So, we are not having the change of the effect of this variation of my altitude, and you can see with the increase of my flight speed, my ram drag that is what is increasing. Now, let us try to analyze the total or say my gross thrust, that is what is nothing but my momentum thrust and my pressure thrust. So, if we look at this, it says it is representing the summation of my thrust because of pressure and the thrust because of my momentum, and you can see this is what is representing the summation. So, let us try to put this in overall sense. What we mean by overall sense? Let us see. So, I will be putting my flight speed versus my thrust, and this thrust we are representing here. So, here if we will try to look at, this is what is representing my gross thrust and this line that is what is representing my drag. So, let us try to understand this plot. Suppose if I consider at particular altitude, we can say with the increase of my flight speed, my thrust that is what will remains constant, and here in this case at the lower speed, my thrust generated by the engine will be higher compared to my drag, and this will be increasing with increase of my speed. Once it will be reaching to high speed, we can say this is representing our cruise condition. Now, at that condition, my drag and my thrust they both will be equal. Now, with the change of altitude, we can look at that is what is asking for say higher flight speed in order to meet the requirement. So, the equation, the fundamental equation by this we need to analyze what all are the effect of these parameters. So, now we are moving towards the detailed analysis of our thrust equation. And initial case we are assuming mass flow rate, that is what is not changing. We all know this mass flow rate, that is what is represented in terms of density into area into velocity. Now, when we are considering this density, it says density is a function of my pressure, and we have realized with the change of my altitude, the density and the pressure, that is what will be changing. So, by actual engine condition, that is what will be different compared to what all we are assuming at this moment. So, for today's class, this is what is sufficient. Let us try to sum up what all we have discussed in today's session. So, we have started discussing about the thrust which will be generated by the individual component, and that is what we have verified by taking the numerical. Then we have started discussing about what we mean by our thrust requirement for the different operations. We have analyzed, we have discussed why we are looking for the total property in place of static properties like pressure, temperature, density for our cycle analysis. Then we started discussing about how we will be segregating or how we will be understanding our thrust equation as individual terms, and this thrust we have analyzed, we have divided, we have segregated in three formation. It says my momentum thrust, momentum drag or ram drag, and my pressure thrust. So, here we are stopping with. In next lecture, we will be discussing about the next scenario where we will be having the variation of mass flow rate. And this mass flow rate that we have discussed is a function of my density and the pressure. So, we will be going in more detail in terms of realizing the actual engine thrust calculation. Thank you very much for your kind attention.